All right, so we have a function f of xy is equal to sine x times cosine y. And we're to find the directional derivative at the point pi over 3 comma pi over 3 in the direction of the vector for negative 3. So we're going to have to find the gradient of f. We know how to do that. And we're going to dot it with vector u. Now remember that u has to be a unit vector. And they gave us the vector for negative 3. It's not a unit vector. So the first thing I'm going to do is convert that vector v into a unit vector. All right, so I'm going to do this off to the side over here. All right, so our unit vector is going to have to be the vector v divided by its own magnitude. All right, so we're going to take our vector. I'm going to switch over to bracket notation for negative 3, and I'm going to divide that by its own magnitude. So it's going to be 4 squared, 16, and negative 3 squared is 9. And that's a beautiful magnitude, all right, because it's the square root of 25, so 5. So we're going to be dividing each component by 5 to get our unit vector. Okay, so that's the vector that's pointing in the same direction as v. It's just got 1 unit long. All right, so we're going to dot that vector, looking down at our red box, we're going to dot that vector with the gradient at our point. So let's calculate the gradient. All right, so our gradient, we're going to take the partial derivative of sine x times cosine y with respect to x. So when I'm taking the derivative of my function with respect to x, the cosine y is just a constant. So I take the derivative of sine x, which is cosine x. But the cosine y was just a constant, so we're just going to leave that as cosine y. All right, gradient in the second component, we take the derivative with respect to y. So back up to my blue bracket. Now the sine x is the constant. And derivative of cosine is negative sine. So we're going to have times negative sine y. All right, so let me put that negative out front so it's easier to look at. So we've got our gradient function, cosine x, cosine y, comma negative sine x, sine y. Okay, so that's our gradient for every single point on the whole surface. We're only interested in what the gradient is doing at the point where x is pi over 3 and y is pi over 3. So let's actually plug that in to our gradient function. So we're going to plug in pi over 3, comma pi over 3. And I get a whole bunch of sines and cosines of pi over 3. So cosine pi over 3, cosine, they're both pi over 3. And then negative sine pi over 3, sine pi over 3. All right, unit circle time if you don't have that memorized. Cosine of pi over 3 is 1/2. So I'm going to have 1/2, comma, no, not comma, times 1/2. Then I've got negative sine of root pi over 3 is root 3 over 2. Sine of pi over 3 is root 3 over 2. And so I get 1/2 times 1/2 is 1/4. And root 3 times root 3 is 3. So I've got negative 3 over 4. All right, so that's my gradient at the point that we're interested in. And I have my unit vector. So our formula says that the directional derivative in the direction of u of our function f is going to be our gradient vector dotted with our unit vector, which we found was 4/5, negative 3/5. Okay, so a lot of fraction multiplication, right? I've got 1/4 times 4/5, multiply component-wise, and then add negative 3/4 times negative 3/5. All right, I could cancel out those 4s, but I see a common denominator coming, so I'm going to leave it. Multiply across the top, I get 4 over 20 plus 9 over 20. And then I've got the common denominator. I can add them, 13 over 20. Okay, so like I said, directional derivatives are going to be scalars. We got 13 over 20. Let's go over to GeoGebra and think about what this actually means. All right, so here's our surface, sine x times cosine y. And we were given the point pi over 3 comma pi over 3. So let me turn that point on. So this is the point that's down in the xy plane. You can see that's in the xy plane. It's not on the surface. Okay, so the directional derivative does go up to the surface. We've got that point on the surface that's right above that point that was given to us. Okay. And what it does, it takes that vector u that we were given, which is an R2, so that's down in the xy plane with the point A, and it says, what is the function doing? What is the z coordinate doing in that direction? So it's going to look at the tangent line in that direction. All right. And it's going to say if I go 1 unit in the direction of u, okay, so I'm going to put that vector there. So from B, it's going to travel 1 unit in the direction of u. How far does it have to change z coordinates to stay on that tangent line? Okay, and that is that distance right there. Okay, so at that point along the tangent line, it's kind of a slope, right? If we go 1 tick mark in the u direction, how much do we have to change our z coordinate to stay on that tangent line? And we have to change it by a y coordinate of 13/20 z tick marks. And that's what the directional derivative is telling us.